Hello and welcome back to the Deep Dive. I want to start today with a question about something you've probably seen, 1,000 times, but maybe never really stopped to question.
Okay.
Think about the dry season. Maybe you have an iron gate outside or an old bicycle chain just, lying in the shed. It stays fine for weeks, maybe months even. Looks shiny, feels solid, nothing really happens to it.
It remains stable, yes.
Yeah, exactly. But then the monsoon starts. It gets wet, a bit warm, humid outside, and suddenly that same piece of iron, the exact same metal, it starts rusting in just a few days. It turns all orange and flaky almost overnight. I mean, it's the same iron, the same air, more or less. So
Yeah.
why is the speed so different?
That's a very, very relatable observation. And that difference in speed, why some things happen in a blink and others take, a century, that is exactly what we're here to discuss today. We're doing a deep dive into Unit 3, Chemical Kinetics.
Unit 3,
Specifically, we're focusing on the factors influencing the rate of a reaction.
chemical kinetics. This is a heavyweight chapter for Class 12 students, I know. A lot of students find the numericals a little tricky, but the theory is, well, it's fascinating.
It is. And today's mission, it isn't just about helping you score marks in your board exams, though we will definitely cover what you need for that. It's about understanding why we care. I mean, in the real world, we're obsessed with speed. We're either trying to hit the accelerator or we're trying to slam the brakes.
Right. So give us the stakes here. Why does it matter if a reaction is fast or slow?
Well, think about medicine. If you are a pharmaceutical company and you're making a life-saving drug, time is money. If the reaction takes 10 years to happen, well, nobody gets the medicine, or it becomes incredibly expensive. You need to speed it up.
Okay, so that's hitting the accelerator. What about slamming on the brakes?
Food. Think about food. If you're packaging milk or potato chips, you want that spoilage reaction to be as slow as humanly possible. You want that food to stay fresh on the shelf for a long time.
So we are literally trying to manipulate nature's clock.
Precisely. And without the concepts we're discussing today, you can't really distinguish between a fast reaction and a slow one in any numerical way. You'd just be guessing. We need to know the specific levers we can pull to control that speed.
Okay, let's unpack this. If I want to control this clock, what's the fundamental rule? I mean, at a zero level, what actually determines how fast a reaction goes?
At the absolute simplest level, you just have to remember one thing. Reactions are, they're violent. A reaction only happens when reactant molecules collide with each other, and this is the key. They have to collide with enough energy.
So it's a contact sport.
100%. If they don't hit, they don't react. So to control the speed, we just have to control the collisions. And we have 5 main levers for this: concentration, temperature, pressure, which is mostly for gases, surface area for solids, and finally adding a catalyst.
5 factors: concentration, temperature, pressure, surface area, catalyst. I want to visualize this because lists can be boring, but a mental image, that sticks. So I want you, the listener, to just close your eyes for a second. Imagine you're trying to get onto a local metro train or a crowded subway.
Ah, a classic experience for anyone in a big city.
Now imagine it's rush hour. This is high concentration. People are packed shoulder to shoulder. You literally cannot move without bumping into someone, right?
Right. High concentration equals high crowd density.
Okay, now flip the scene. It's 3 in the morning. The train is running, but the compartment is almost empty. This is low concentration. You can walk from one end to the other and probably not touch a single person.
That is a perfect mental model for what's happening inside a beaker. When we say high concentration, it's just rush hour for the molecules. They are packed so tightly, and because they're packed, they bump into each other constantly. More bumps, more collisions means a faster reaction.
And at 3 a.m.,
Low concentration, there are huge gaps between the molecules. They just wander around, but they rarely meet, and if they don't meet, they can't react, so the whole process just crawls.
that makes perfect sense for how often they hit. But you added something earlier. You said they have to hit with enough energy.
Yes. And this is where students, they often get tripped up. It's not just about bumping, it's about bumping effectively.
What?
Think of it like a bumper car ride at a fun fair. If you just gently nudge another car, nothing really happens, you just bounce off. But if you slam into them at full speed,
Crash.
exactly, you might break parts. You cause a reaction.
So we need a violent crash, not a polite nudge.
That's it. We call that the threshold energy, or activation energy. So changing factors like temperature isn't just about moving things around, it's about giving those molecules the energy to actually break their existing bonds when they crash so they can form new ones.
Okay, before we go deeper into the physics of the crash, let's just anchor this for the students listening. If you're in an exam hall and the question asks, what factors influence the rate of reaction? What's a definitive list?
You need to write down these 5. Very clearly. Concentration, temperature, pressure, surface area, and catalyst. It's a simple list, but you must remember all 5 for full marks.
Is there a hierarchy here? I feel like students often assume these are all equal levers. Like if I double the concentration, it's the same as doubling the temperature.
That is the biggest misunderstanding trigger we see. These factors are absolutely not created equal.
Okay, so which one is the boss?
Temperature is king. It has the most dramatic, the most exponential effect. The general rule of thumb, and this is a great fact to quote in your exam, is that for every 10 degrees Celsius rise in temperature, the rate of the reaction usually doubles or even triples.
Just 10 degrees. That's the difference between a pleasant morning and a slightly warm afternoon.
Yes. It is a small shift in condition for a massive jump in speed. Concentration, on the other hand, is usually linear. You double the stuff, you roughly double the rate. But temperature, it's explosive.
We need to unpack why temperature is so powerful in a minute, because that sounds a bit counterintuitive. But first, let's build a stronger mental movie for how all these factors play together. We did the subway, but let's try another analogy, the traffic intersection.
This is a great way to visualize the chaos. I want you to think of the rate of reaction as the number of, let's say, car crashes happening at a busy intersection every hour.
Okay, little dark, but I'm with you. The goal is to cause crashes. So if we talk about concentration.
Higher concentration is simply putting more cars on the road. If you have 100 cars passing through per minute versus 10 cars, well, statistically, you're going to see more crashes.
Makes sense. Now, apply temperature to this.
Higher temperature is like the speed limit. Low temperature is a school zone. Everyone is driving at 20 kilometers. Even if they hit, it's just a scratch. But high temperature, that's everyone driving at 100 kilometer. Now, not only do they crash more often because they're moving so fast, but when they do hit...
Total destruction.
Exactly. The collision is effective, the bonds of the car break. That force is the energy we were just talking about.
Okay. What about the catalyst? Where does that fit in a traffic jam?
A catalyst is like a brilliant city planner stepping in. Maybe they build a tunnel or install a smart traffic light system. The number of cars, the concentration is exactly the same. The speed, the temperature is the same. But because the path is easier or better organized, the cars get through the process much faster.
I like that. A catalyst doesn't add more cars. It just it removes the friction. It makes the route efficient.
Precisely. It lowers the barrier to success.
Now, surface area. This is specific to solids, isn't it?
Yes. Imagine our intersection again. Right now, it's a single-lane road. Very little space for cars to interact. Increasing surface area is like widening that intersection to 10 lanes. Suddenly, there is so much more exposed road where cars can hit each other.
And finally, pressure for gases.
Think of pressure as simply squeezing the space. Imagine a giant stepping on the city and pushing the buildings closer together. You're narrowing the lanes, forcing the cars into a tighter box. Even if they don't want to hit, they have nowhere else to go.
So high pressure forces collisions just by removing empty space. That's a very clear picture. Whether it's cars or molecules, we're just manipulating two things, how often they meet and how hard they hit.
That is the core of it. And you might ask, why did we bother figuring all this out? Why do chemists care so much about this?
Yeah, aside from passing class 12, why does this matter?
Because nature is just inconsistent. Some reactions are glacially slow, like that rusting gate. Others are instant, like an explosion. So by the late 1800s, chemists realized they needed to tame this. They saw that heating things up made reactions faster, and diluting them slowed them down. And that led to the development of rate laws.
So it really is the science of control.
Completely. Think about a factory making ammonia for fertilizer. We'll talk about that in a bit. If they get the temperature just slightly wrong, they lose millions of rupees because the reaction is too slow. Or even think about that best before date on your milk packet.
How is that related?
That date is a calculation. Food scientists know the rate at which bacteria will spoil milk at refrigerator temperatures. They use these exact kinetic factors to predict when the milk will go bad. Best before is literally a chemical kinetics prediction.
Wow. That's fascinating. I will never look at a milk packet the same way again. Now, I want to give the listener one more visual just to lock this in. We've done the subway. We've done the traffic jam. Let's imagine a factory floor.
Okay, a manufacturing plant.
The workers on the floor are the molecules. And their job is to take part A and part B and smash them together to make a product.
Right.
So we have low concentration and low temperature. What does that look like?
The workers are scattered far apart, maybe one worker every 50 feet. And because the temperature is low, they're lethargic, they're moving in slow motion, maybe tired, cold. They barely interact. Production is near zero.
Now let's crank it up. High concentration and high temperature.
Now the floor is packed. Workers are shoulder to shoulder, and because it's hot, they are highly energized. Maybe they've had 5 cups of coffee. They are sprinting around, grabbing parts, bumping into each other, passing materials.
You just see the raw materials, the reactants, turning into finished products at a crazy speed.
Yeah,
The factory would be buzzing.
exactly. And if a catalyst walks in,
Ah, the catalyst. It's like a smart supervisor who walks in and says, hey, stop carrying the heavy boxes over that hill. Use this conveyor belt instead. The workers don't necessarily move faster. They don't use more energy, but they finish the job quicker because the path is easier.
that is a perfect description. The catalyst provides an alternative pathway with a lower activation energy. It changes the route, not the workers.
So we have the theory, we have the visuals. Let's look at some real-world examples. We started with the rusting iron. Let's break that down scientifically now. Why does the monsoon kill my gate?
It's a double whammy, really. Let's look at the data. In dry air at 25 degrees Celsius, iron might take months to show visible rust, but in wet air at 50 degrees Celsius, it can happen in hours or days.
Is it just the water?
It's 2 factors working together. First, the moisture. The water increases the concentration of reactive species on the surface. It provides a medium for the ions to move around. Second, the heat. 50 degrees is a higher temperature, and as we know, that increases the collision energy, so you have more ions moving and they're hitting each other much harder.
So my gate doesn't stand a chance.
Not without a good coat of paint to block the surface area.
Good point. Now for a huge industrial example, the Haber process. This is how we make ammonia for fertilizer.
This is a critical one for exams and honestly for human survival. Without the Haber process, we couldn't grow enough food to feed the world.
And nitrogen is pretty stubborn, right? It doesn't like to react.
Nitrogen is incredibly lazy. It has a triple bond that is very, very hard to break. So engineers have to, well, they have to throw the kitchen sink at it using kinetics.
How do they use our 5 factors?
They use high temperature, around 450 to 500 degrees Celsius, to give the molecules enough energy to crash and break those bonds. They use high pressure, 200 atmospheres, to squeeze the gas molecules together so they hit more often.
And I assume they don't just wait around for nature.
No, of course not. They use an iron catalyst. This gives the nitrogen and hydrogen a surface to stick to, making it easier for them to find each other and react. So, high temp, high pressure, catalyst, the holy trinity of making ammonia.
It's amazing that we have to torture these molecules with that much heat and pressure just to get them to cooperate.
That is the reality of industrial chemistry. It's a brute force application of the rules we've just learned.
Now, I want to circle back to something we touched on earlier. You said temperature is the boss. I want to challenge the listener with something that, well, it feels wrong.
Go ahead.
If I'm running a factory or a reaction and I want to speed it up, my gut tells me just add more stuff. If I double the concentration, put twice as many people on the train, that surely must be more effective than just raising the temperature by a tiny bit, say 10 degrees.
That's a very natural assumption. You think double the quantity, double the speed. It's linear thinking.
But you're saying that's wrong.
In kinetics, yes. Raising the temperature by just 10 degrees Celsius is usually much, much more powerful than doubling the concentration.
But why? Why does a little bit of heat beat a lot of concentration?
Because concentration just increases the number of collisions. It's a numbers game. But temperature, it increases the energy of every single collision exponentially.
Exponentially.
Think of it this way. That subway train again. Doubling the concentration is like shoving twice as many sleepy people into the car. Sure, they'll bump more. But if you raise the temperature, it's like giving every single person a double shot of espresso and telling them to run. Suddenly, every bump is a knockout. The fraction of people with enough energy to react just skyrockets.
That's a great distinction. Concentration adds bodies. Temperature adds chaos. And chaos drives reactions.
Energy beats numbers. That's the takeaway.
Okay, we've covered a lot of ground, but we need to make sure our student listeners are ready for their exams. Let's do a quick clarity check. I'll say the topic, and you give us the strict exam-safe rule.
Let's do it.
First up, concentration and temperature. What's the rule?
Simple rule. Concentration and temperature always increase the reaction rate. Never decrease. And remember, for gases, pressure behaves just like concentration. Higher pressure means higher concentration.
Next, surface area.
This is important. Surface area only matters for solid reactants. Do not talk about surface area for gases or liquids in this way. A powder reacts faster than a chunk because it exposes more surface for collisions.
Okay. The catalyst. 2 rules here.
Yes. 1, A catalyst speeds up the reaction but is not consumed. You get it back at the end. 2, it does not change the equilibrium position. It speeds up the forward and the backward reactions equally. It just gets you to the finish line faster. It doesn't change where that finish line is.
That is a crucial distinction. It saves time, not distance.
Oh,
Okay, and let's just reiterate.
yeah.
The power of temperature.
Yes. Temperature is the most powerful factor. It exponentially increases the fraction of effective collisions. If you are writing an exam answer about temperature, you must use the word exponential.
And finally, a big one. How do we know the order of reaction? Can I just look at the equation?
No, the order of reaction is determined experimentally. You cannot just look at a balance equation and guess. You have to do the experiment.
Perfect. Those are your safety lines. Write those down, and you are safe. So let's wrap this all up. A short summary. If the listener takes away just 4 points from today, what should they be?
To recap, number 1, the core idea. Rate is all about collision frequency and energy. If they don't hit with enough force, they don't react.
Number 2, the mental picture. Think of the traffic intersection or that crowded subway. More people or faster cars. It just means more crashes.
Number 3, the real world. We use this science to force nitrogen to become ammonia for fertilizer, or to understand why moisture makes our gates rust.
And number 4, the golden rule.
Temperature is king. It has an exponential effect on energy, and catalysts are the smart supervisors that show us the shortcut without being used up.
That covers it beautifully.
Now, before we go, I want to leave you with one final thought to chew on. We talk a lot about speeding things up, faster, faster, faster.
Right.
But here's something to think about. If temperature makes reactions faster, why do we sometimes purposely cool reactions down in the lab? Why do we pack reaction vessels in ice?
Interesting. I assume it's not just to keep the drinks cool.
No, we do it to prevent explosions. It's something called thermal runaway. If a reaction gets too hot, it goes too fast. Because it goes fast, it releases more heat. That heat makes it go even faster. It becomes a self-feeding loop until, well, boom. So sometimes mastering kinetics means knowing when to use ice, not just fire.
That is a very cool thought to end on, pun fully intended. Mastering these 5 factors means you've mastered the basics of kinetics. Thank you for listening, and good luck with your studies.
Good luck, study hard.